Hello everyone, and welcome back to another GIS lecture video. And in this lecture video, I want to continue our discussion on spatial data models by taking a step in a different direction and talking about the raster data model. But before we jump into that, I wanted to take a second because we've covered a lot of stuff here, and I wanted to just kind of go back through and recap the things we've talked about. So up to this point, we've sort of broadly introduced vector and raster data. We introduced the points, lines, and polygon geometry forms of vector data. So that was based on the number of coordinates that the data had and whether or not it formed a closed loop for point versus line versus polygon. We talked about the idea that vector data had geometry, which was points, lines, and polygons, but it also had attributes that were stored in an attribute table that were connected to the geometry via an ID. And then most recently, we talked about this idea of topology, which is basically rules that we inform the computer about that the computer then enforces on the data to keep the data clean in a way that we would expect it to be based on what we would think of in the real world. And we also touched on this idea of multi-part versus single part, where with single part, you had a single row in the attribute table being represented by multiple pieces of geometry, versus multi-part, each individual geometry piece was represented by its own row in the attribute table, even if it was the same sort of real-world feature. And we used the example of the Hawaiian Islands, right? Each island could be its own record, even though they're all Hawaii, or Hawaii could be a record, and all of those islands would be associated with that. So hopefully all of that made sense. Hopefully nothing I said was a shock or new to you. If it was, I encourage you to go back and watch those particular videos. Because now we're going to jump over to a different way to represent data, spatial data. And that is with the raster data model. So we've already kind of dealt with raster data when we went through that first example of fire hydrants. But what we do with raster data is, instead of having individual features with their own coordinates, what we do is we take an area and we break that area up into small, evenly sized squares. Oops. My evenly sized part is going out the window as I draw here. But, right, the idea is that we take an area and we break it up into small, evenly sized squares. And then for each of the squares, right, we sample the world for whatever it is we're trying to do, right? If it's fire hydrants, right, we would sample this area and say, is there a fire hydrant? If there is, mark it. If there isn't, don't, right? Then go on to the next cell and do the same thing, right? What is the status of the thing that we're trying to investigate? Whatever that status is, mark it. Now, here is why we might want to use raster data as opposed to vector data. Think for a second about something like weather patterns, right? Or precipitation, right? How much area or how much rain does a particular area get, right? It is certainly possible that you could have individual weather stations scattered across the area, right, represented by points with an attribute that would say how much rain did that particular point get you. You could certainly do that. Alternatively, what you could do is you could take raster data, a raster data set, break that whole area up into evenly spaced grid cells, and then for each grid cell say, how much rain did this little area get? Mark that down. How much rain did this area get? Mark that down. How much rain did this area get? Mark that down. And so with raster data, right, you can measure things in a continuous scale over areas, right? I'm going to make a note of that, right? Raster data can measure continuous data, or not use data, continuous, we'll say phenomena, right? This is a thing you're interested in. It could be the presence or absence of fire hydrants. It could be the amount of rain an area gets. It could be elevation, right? It's anything that you're interested in measuring, right, over an area. And I want to highlight the word continuous, right? When we talked about vector data way back in sort of the beginning of the lecture series, right, we talked about this idea of discrete, right? Things that had clear specified boundaries. Those boundaries were represented by coordinates. Those coordinates were mapped, and they were connected to their attributes via an ID. Raster data doesn't work that way, right? Raster data takes the whole area that you're interested in looking at, breaks it up into these little boxes, and then measures whatever it is in each box, right? And that's why I said, okay, imagine, right, rainfall. Rainfall changes, right? You could have a weather station, walk 5 feet, and get a completely different result over a very small distance, right? There's no defined boundary on rainfall, right? That's the best way to think about it, right? There's no defined boundary on rainfall. So something like a raster data, right, being able to measure it, move a little bit, measure again, move a little bit, measure again, move a little bit, measure again, right, gives you that continuous nature, right? Because there's no boundary here in raster data, right? I mean, there is, it's artificially constructed by the cell size, but we'll talk about that in the next video. But the idea with raster data is that you can represent something that changes continuously by, instead of having these discrete locations, simply saying, hey, we're going to just measure at every location to generate a series of grid cells that represent whatever that phenomena is. So the point of this video was more so to talk about the structure. So let's peel back a little bit from that tangent. And let's talk about the actual structure here. What does raster data look like in terms of how it's structured? So we kind of already drew a picture here. So let's continue with this. Right, so at the most fundamental level, right, we have this box right here. Right, this box, depending on who you talk to, will be called either a pixel. This is more of a remote sensing term. And don't worry, we're going to come to remote sensing in great detail towards the end of the semester, which deals almost exclusively with raster data. Or you'll sometimes see it referred to as a grid cell, or just a cell. Right? So either way, this idea of a pixel or a grid cell, right, this is the smallest unit of the remote sensing data structure. Right, and it's a small, it's basically a square that holds a value. Right, so we'll talk about the value in a different video, right? But inside of this pixel, right, there's what's called the value. And this value is the attribute. We'll talk about that in more detail later. Right, so then if we expand out, right, and we look at a horizontal collection of pixels or grid cells, right? So I'm going to take orange here, right? If we look at a horizontal collection of pixels or grid cells, right, we call that a row. So a row is a horizontal collection of grid cells. Let's see if I can make that a little bit clearer. Right. Conversely, right, if we look at a vertical collection of grid cells, right, that's called a column. Right? This vertical collection is called a column. If we take the entire thing in its entirety, this is all the rows, all the columns, right? This is the raster. And we'll talk about in remote sensing a little bit more terminology. But for now, this is really the heart of it, right? We have an individual square representing a small area of the world. We call that a pixel or a grid cell. Inside of that, we have some value that represents whatever it is we're measuring, whether it's rainfall or elevation or whether or not there's a fire hydrant there, right? We call that the attribute or the value. If we look at how the pixels are arranged, right, they're arranged in rows and columns. And if we take everything together holistically, that's the raster. So hopefully this makes sense. And as always, if you have any questions, please reach out. Thank you.